Today we will continue to talk about some of the more detailed issues regarding the FDTD simulation. And in particular, we'll be talking about the issue related to numerical dispersion. So as an illustration of the issue, we go back to an example that we have considered in the previous tutorial, that is to compute transmission of light plane wave normally instant on a silicon slab. In this case, we chose the refractive index of silicon as 3.5, and we chose a thickness to be 0.5 micron. On the right here is the analytic results for the system. And what you see are a series or a set of resonance peaks where the transmission reach 100%. And the frequencies of these peaks can be easily predicted by noting that the round trip phase at each of the peaks correspond to 2 pi. Now, with this, one can also try to simulate it with the FDTD method. And this we have talked about before in the tutorial video number 2. As a brief recap, we put periodic boundary condition in the 4 plane, in the X, Y, and XZ plane, put PML in the top and bottom. We put a plane wave source and then use a pulse to generate a transmission spectrum, to obtain the transmission spectrum in the numerical calculation. So for this system, the blue dashed line here is what we will obtain in the FDTD simulation if we choose a spatial discretization corresponding to 25 nanometer. What you can see is that the result is not too bad. Generally speaking, in FDTD, you also see a series of peaks, but the detailed position of these peaks shifted a little bit from the exact analytic results. Also, if you look more carefully, you can see that the difference between the FDTD and the analytic results is smaller in the low frequency side and gets gradually bigger as you go to higher and higher frequencies. So it would be important when you use the FDTD method to understand where some of these numerical errors come from. In this case, the numerical error actually comes from numerical dispersion that arise due to the discretization of both space and time. So here I would like to give a brief discussion on the issue related to this numerical dispersion. As a way of introduction, it turned out for the problem that we're solving here, normally instant light of a particular polarization in vacuum, for example, you can convert Maxwell equation to a 1D wave equation that looks like this. For this equation, the solution is a monochromic traveling wave or a plane wave solution. This solution has a wave vector K that tells you about the spatial variation of the field, as well as frequency omega that tells you the temporal variation. And the wave vector and the frequency are related by a dispersion relation. And in this case, the dispersion relation is simply a straight line between the frequency and the wave vector. This is physically what we would like to study. Now, in the FDTD simulation, what we do on the numerical side is to discretize this wave equation. So in other words, we represent the spatial derivative operator and the temporal derivative operator using finite difference approximation. In doing so, what we are looking at are wave propagation on a discretized lattice as indicated here, where both the space and the time are discretized. For these lattices in discretized space and time, again, the solution of this discretized system is a plane wave characterized by a wave vector and a frequency. And again, there is a relation between the frequency and the wave vector in this discretized lattice. But the important point here is that this functional form is no longer identical to the dispersion relation of the physical wave. So here is an illustration plotting these two dispersion relations for the physical system and the numerical discretized system. Again, we're plotting frequency as a function of k for these two functions. What you can see is that for the physical system, the omega k relation are straight lines. For the discretized system, the numerical system, at low frequency, or in other words, when the discretization of delta x is small for a given frequency, the numerical wave dispersion is very close to the physical wave dispersion. And that's the regime that you would like to be in, because then the wave propagation characteristic of the numerical system is very similar to the physical system. On the other hand, as you increase frequency for a given discretization, or if you, for a given frequency, use a larger spatial step, then the numerical wave dispersion can deviate from the physical wave dispersion, and in which case you will start to see more significant error. This issue that the dispersion relation of the numerical system is different from the physical system is what we refer to as numerical dispersion. The deviation of the transmission spectrum of the dielectric slab in the FDTD simulation from the exact analytic calculation can be understood by analyzing the numerical dispersion relation. So to highlight the issue of this numerical dispersion, here we choose an even larger spatial discretization. So it's much coarser. Here we choose that to be 15 nanometer. Now you can see that there are substantial differences between the FDTD and the analytic results. In particular, you see the frequency differences of these resonance peak between the numerics and exact analytic results. And these differences can be understood by analyzing the corresponding numerical dispersion relation. So the resonance corresponds to a fixed wave vector where the round trip phase is 2 pi. And you can see that for these resonant wave vector, the frequency differences here correspond to the frequency difference in the dispersion relation between these two systems. And at low frequency, the difference is small. As you increase the frequency, the difference gets larger. And that's exactly what you see here. Smaller error in the low frequency side and larger error in the high frequency side. If you increase the spatial discretization by reducing the spatial time step to 25 nanometer, now you can see that the dispersion relations of these two systems become closer. And also in the transmission spectrum, you see that the peaks location in frequencies of these two systems also become closer. And if you choose the spatial discretization to be 12.5 nanometer, which correspond to about 23 grid points at the wavelengths around 300 terahertz, now you see that the FDTD simulation and the analytic calculation become very close to each other. This is consistent with the fact that in this case, the dispersion relations between these two systems also become fairly close to each other. So to give a more quantitative view of the error that's resulting in numerical dispersion, what we do here is we sample about 300 frequencies in the transmission spectrum here. And then we look at the root mean square error between the transmission from the FDTD results and the transmission from the analytic results across all these frequencies. So here is a plot showing the error as a function of the number of grid points per wavelength of in silicon in the middle of the spectrum that we're talking about in the previous slide. And generally, you see that the error goes down as the number of grid points goes up. And in fact, this is a log plot, and the slope here gives you the exponent of how the error depends on the grid spacing. And this turned out to be a second order scheme, as you can infer from the slope here. The numerical observation here indicates that if you want to achieve an error of less than 1% averaged inside the spectrum, inside the wavelength range that we're talking about, roughly speaking, the number of grid points per wavelength in the middle of that wavelength range is about 30. So that gives you an indication of the numerical dispersion, the effect of numerical dispersion, and the choice of number of grid points that you need to do to suppress the effect of numerical dispersion. So up to this point, we have talked about the effect of numerical dispersion in one dimension. And this comes about from the difference between the dispersion relation in one dimension, and one of the main effects that you see is the shift of the resonant frequencies in the transmission through a slab. In higher dimension, there are additional effects associated with numerical dispersion. So here we illustrate this in 2-dimension, and the 3-dimensional system, the effects are rather similar. So in 2-dimension, again, for the physical system, you have a plane wave solution with a dispersion relation that's indicated here. For the numerically discretized system, again, you have a plane wave solution, but now you have a dispersion relation as indicated by this equation. So you can visualize these dispersion relation in what's called a constant frequency contour plot, where for each frequency, you plot the wave vector value that satisfy the dispersion relation. So for the physical system, at every frequency, the kx and ky lies on a circle, and the radii of these circles increase as the frequency increases. So you get a plot as indicated here, where the 3 contours here correspond to 3 different frequencies. As you increase the frequency, if you keep the discretization fixed. As I mentioned already, alternatively, you can read this as a fixed frequency, but changing the discretization in space as well. Similarly, you can plot this constant frequency contour for the numerical dispersion. And again, you will get a set of closed curves in the kx and ky space corresponding to different frequencies. In this case, for low frequencies, the contour is essentially a circle very close to the physical system. And that's a regime that you would like to be in. On the other hand, as you increase the frequency, or alternatively for given frequency, if you use a coarser grid, you can see that the contour in this case deviate in its shape from the circular shape. And this indicate that the numerical lattice has numerical anisotropy. The phase velocity of the wave propagating along, for example, the x or y axis is different from the wave that's propagating along the diagonal direction here. And this effect you can also see in FDTD simulations. So as an illustration, one can look at the radiation pattern from a dipole. If you take a dipole along the z direction, oscillating at a particular frequency, and look at the distribution of the EZ field in the XY plane on a plane that cuts through the center of the dipole, then you will see cylindrical wave going away from the dipole as indicated here. And the field vary between positive and negative values at a given time in space. And you can define the wavefront by plotting where the field actually goes to zero. So in the ideal case, then these wavefronts are concentric circles centered at where the dipole is. With this, now you can look at the FDTD simulation where you put a dipole at the center of a computational cell. You surround the computational cell by perfectly matched layer. And again, you can look at this wavefront plot, which show you where the EZ field goes to zero at a particular time. So for a given discretization at low frequency, or for a given frequency at a fine resolution, you can see that the wavefront here, as indicated by the black line, is very close to a circle. That indicate there very little numerical anisotropy. The phase velocity in every direction in this plane are very similar to each other. On the other hand, if you increase the frequency for a given discretization, or for a given frequency, you reduce the discretization. In other words, you make the grid coarser. Now, again, you can generate this kind of wavefront plot as indicated by the black line here. And as a comparison, the dash line here, the red dash line here, is where a ideal circle will look like. Now you can see that the wavefront in its shape, in fact, deviates from the circular shape, as you would expect from ideal analytic results. In other words, the phase velocity of the wave along different directions become different to each other. And so in 2 dimension and as well as in 3 dimension, one of the effects of these numerical dispersion is now the numerical anisotropy corresponding to wave propagate along different directions having different phase velocities. So with that, let me briefly summarize. A key source of error in finite difference time domain simulation is the issue of numerical dispersion. This comes about because the dispersion relation or the velocity of the wave in the discretized lattice is not identical to that of a physical system. As a general rule of thumb, to suppress numerical dispersion, you will need a finer grid. And as from experience, typically to have acceptable or relatively small numerical dispersion error, a spatial discretization less than the wavelengths in material divided by 20 is usually sufficient for many of the simulation. However, it is important to really keep this kind of issue in mind as you design your simulation. Thank you for your attention.